Okay, thank you very much, both to the organizers and the local organizers, for creating this wonderful opportunity. So indeed, I will talk about non-singular Bernoulli actions. So what is the general setup and the general question? So let's look at the following very basic problem, namely the standard Bernoulli shift. So single transformation, we are looking at a product probability space x mu. So we have a base set x0 and we take it infinite product index by z and we shift. And of course this is the well-known Bernoulli shift, except that we make one distinction with the classical well-studied case, namely we allow the base measures mu n to vary when n varies. So then we will have to make sure that the shift is still non-singular, so that the shift still preserves sets of measure 0. And in order to preserve sets of measure 0, at least we need that these measures are all equivalent, that individually the measures mu n have the same sets of measure 0. That will not be sufficient for non-singularity of the shift. We'll come back to that later, but at least that's something we need. Now, the big question that we want to address is which injective factors can arise as the cross product by such a Bernoulli shift. Now, of course, they're all injective because that is amenable, and by the classification of amenable factors, due to Kohn, Heurup, and then also Krieger to look at type 3.0 case, the real question is what are the possible types and what are the possible associated flows of these factors. And of course, we can get hyperfinite to 1 by just repeating the same base measure on a non-trivial set x0. Now, this has a certain history in the sense that the question was first addressed in the early 1980s by Hamachi, who proved a kind of existence result, in the sense that he proved that there could be choices of mu n such that the shift is of type 3, ergodic and of type 3. And then, much later, Kozlov could make much more precise calculations and show that the shift can be that there exist shifts of type 3.1. Now, both are a kind of existence theorems in the sense that the way they prove this is by actually taking for x0 as just a set with 2 points and then inductively choosing mu n plus 1 in terms of the previous ones and doing that carefully, showing that if you follow this inductive procedure, then at the end you get type 3.1. I was just telling you this because these early results, they are not at all looking at the shift in general and saying what can be the type of such a general shift. I mean, it's really constructing examples. Now, the first really systematic results on ergodicity and type of such a shift has been done by Michael Björklund, Semir Kozlov, and myself a few years back. And one of the surprising things we proved is that if you take for the base set just 2 points, or for that matter, a finite set. I mean, 2 points or a finite set will not be very distinguishable. If you take just 2 points as a base set x0, then actually type 2 infinity cannot be reached. Whatever, in full generality, no further assumptions on the measures mu1. It can never be ergodic of type 2 infinity. So that was the first, say, no-go result, the first in full generality no-go result. Then, at the same time, and independently, Kozlov and so, and then my student Tey Berendschot and myself, we proved in a constructive way that all type 3 lambda may arise except for lambda 0. But in our paper, Tey Berendschot and myself, we also could reach type 2 infinity and some type 3 0. But this is again on the more constructive side, say, in the sense that we did have some general results on but not for fully general shifts. Now, the interesting thing is that, for instance, so you can get a shift of type 2 infinity, you cannot get it with a base space of 2 points, but you can already get it with an infinite discrete base space. So the phase transition there is really from a finite set to an infinite set, not to the continuity of the measure set. And then, more recently, in a recent paper of Tey Berendschot and myself, we proved that there is actually a general obstruction, so that not all type 3.0 are reachable by non-singular shifts. And that's what one of the things that I want to explain today, in the sense that not all can be reached, but many can. So it's not just a few type 3.0, a lot of type 3.0 can be reached. So most of what I will be telling today is actually from these joint papers with Tey Berendschot. But let me now take a few steps back and give a very quick introduction to what is the type and what is the flow of such a non-singular action, if you have somehow forgotten about this. So the type, I guess, many of you are familiar with. So if you take any non-singular action, so preserving sets of measure 0, then we will say that it's of type 2-1 if there is a G-invariant probability measure. So by the way, let's assume that the measure is not atomic. So let's rule out the type 1 case all the time. Type 2-1 if there is an invariant probability measure equivalent to mu. Type 2 infinity if there is an infinite measure that's invariant under the action and equivalent with mu. And then type 3 are all the others. And then we need some variants of modular theory to distinguish between the different type 3s. So that is modular theory in the ergodic sense of the word is Krieger's associated flow, and it goes in the following way. So since the action is non-singular, it is preserving sets of measure 0, so we can look at this Radon-Nikodym derivative, measuring somehow the lack of invariance of the measure. We take the logarithm of the Radon-Nikodym derivative, and the result is a 1-cos cycle for the action with values in the real line. Now, having such a 1-cos cycle, you can make a skew product action. So because of the 1-cos cycle relation, this formula defines an action of G on X times R. It's called the Maharam extension of the original action of G on X. And this Maharam extension will, by construction, automatically be infinite measure preserving. Namely, by construction, it preserves the measure mu times, not times Lebesgue, but times e to the minus SDS. That's the right measure to take. And also by construction, this Maharam extension action, this skew product action, commutes with translation in the second variable. So that's true by construction. Now, what one does is then taking the ergodic decomposition of the G action. So you take, say, this largest G invariant factor map. So you take the ergodic decomposition of the action, realizing the G invariant functions on X times R. And then because the R action was commuting with the G action, on this factor, on this ergodic decomposition, we get an action of the real line. And this action of the real line, if the original action was ergodic, will be an ergodic action of the real line, because indeed, if you're both R invariant and G invariant, then the function will not depend on this second variable, and then by ergodicity of G on X, also the function must be constant almost everywhere. So we have this associated flow. It's due to Krieger. It's called Krieger's associated flow. And of course, people in modular theory will recognize this also as the Kohn-Takazaki flow of weights of the cross product. So it's exactly the same thing. Yeah, that's a straightforward thing to compute. Now, this is then closely related to the division in subtypes due to Alain Kohn. So again, take your essentially free and non-singular action. Type 2-1 and type 2 infinity, so the semi-finite case, is exactly characterized by the associated flow being just translation action of the real line on itself. The type 3-1 case is when the associated flow is trivial, meaning that the Maharam extension remains an ergodic action. Type 3 lambda is the case where the associated flow is periodic. So when it has this period, so it's the translation action on R mod Z log lambda, then the action is said to be of type 3 lambda. And then type 3.0 is just the big box with all the remaining cases where the associated flow is a properly ergodic flow. And this, of course, exactly corresponds to Alain Kohn's types of the cross-product factors. And then, due to a lot of work, these are complete invariants for these cross-product factors in the case where G is amenable. Okay, so this was this quick introduction to associated flow and the types. So let's now go back to Bernoulli shifts. So here is again the setup. We look at this general shift without any further assumption, except that we have to assume that the shift is non-singular, and I will come back later to what it means technically. I mean, there is an if and only if condition on the measures mu n for this shift to be non-singular. And also let's assume that it's not atomic. That's very easy to see what the condition on mu n has to be. And then let's further assume that the action is ergodic, and this is not automatic. So I will also come back to that. So what happens in this case? Actually, the two things that Tey Berendschot and myself proved can be summarized as an obstruction result and a construction result. So on the obstruction side, what we proved, and I will explain you how this goes, is that for such a Bernoulli shift, the associated flow must automatically have a dynamical property that we call infinite divisibility. I will immediately present you the definition. And it turns out, that's not our work, that not all ergodic flows are infinitely divisible, while all ergodic flows are the flow of a type 3-0. So you cannot reach everything because of that obstruction result. Then on the construction side, we introduce a notion of Poisson flows, and then we prove that actually all Poisson flows do arise as the associated flow of a non-singular Bernoulli, and the class of Poisson flows is pretty large because it actually includes all almost periodic flows. So if you let R act on a compactification, that is an example of a Poisson flow. And in the end, I will also discuss the connection with ITP of 1, 2 factors. So these are the type 3 factors that you can write as an infinite tensor product of 2 by 2 matrices. So what is this property of infinite divisibility? Well, it's related to the following notion due to Hamachi, Oka, and Nozikawa, and it's a construction of the joint flow. Now this will look a bit ad hoc, but in a minute you will see that it's actually very natural. So it's a construction that, given a finite number of ergodic flows, so ergodic non-singular actions of the real line, constructs a new ergodic flow of the real line that we call the join of these n ergodic flows. How is this constructed? So first of all, you take n copies of the real line in direct product, so we call this H, and then we look at the product action on the product of the spaces. So just the first R acts on Y1, the second R acts on Y2, and so on. Now in Rn we have the kernel H0, which is the kernel of this natural homomorphism to the real line, and that's of course a closed subgroup, and by definition the joint flow is defined as the action of the quotient, which is of course through this isomorphic with R, on the H0 invariant functions. So it's immediate to see that this is again an ergodic flow, and it is somehow natural in the sense that if you look at this H0, it's of course generated by, if you take 2 of the copies of R and you put a T in one copy and a minus T in the other copy, that is of course generating this kernel, and then actually this is like saying that you look at the largest factor where the action on any of the variable is the same action. So whether you act by T, whether you translate by T in the ith variable or in the jth variable, but by construction, in this factor, this is the same action. So that's where it somehow gives you a natural flavor of it. But it's even more natural because it's an easy observation that this just corresponds to the flow of weights of the tensor product factor. So if you have a tensor product of n factors, each of them has its flow of weights, then the flow of weights of the tensor product is, by construction, just the join of these n flows of weights. So it's kind of a natural thing to look at. And then in view of the Neumann algebra literature, it's quite natural to say that an ergodic flow is infinitely divisible if for any n it happens to be isomorphic to the join of n identical copies of a certain flow. So in terms of the injective type 3-0 factor, it means that your factor m can be written as a tensor power of a given type 3-0 factor, where the tensor power can be as large as you wish. So that's the definition of the joint flow and this notion of infinite divisibility. Now, before linking it to Bernoulli actions, let me move out of the way a few of the trivialities that may happen with these non-singular shifts. Yeah? So first of all, there is the non-singularity condition. So if you take any shift like this with all the mu n's being equivalent, that's an obvious, having the same null sets, that's an obvious condition. Then by the Kakutani criterion on the equivalence of infinite product measures, it's very easy to see that this is preserving sets of measure zero, so it's non-singular, even only if the following condition holds. So somehow the mu n plus 1 should be close enough to mu n, so the distance squared of mu n plus 1 and mu n should be summable. And here you measure the distance in so-called Hellinger distance, and the Hellinger distance, the formula is written here. It is actually the L2 distance between the square roots of the Radomir derivatives. So it's an L2 distance. Okay, and here formally you would also consider the Hellinger distance if measures are not equivalent. So you would just pick any probability measure zeta that such that mu and mu prime are absolutely continuous with respect to zeta, and then you can compute this, and it's immediate that it doesn't depend on the choice of zeta. Okay. Now, for a non-single Bernoulli action, here are two trivialities that may occur. The measure could be atomic. That, of course, you can rule out by the obvious condition on the mu n. But then, and this is more tricky, the shift could be dissipative, which by definition for these essentially free actions means that there is a fundamental domain. So it may be of type 1, so having a fundamental domain that just disjointly moved by the action. And for instance, that's an observation also of Hamachi. This is quite common. Well, for instance, here, if you take for the Z action, all negative mu n to be mu minus, all positive mu n to be mu plus, with mu minus and mu plus different, then this is always of dissipative. So it does happen, and of course, in terms of which factors you can reach and types and so on, this is totally uninteresting. This is the type 1 case. We have to assume that we are not in this situation. Yeah? And I will come back to say sufficient criteria that assure you that you are not in this situation. Okay, if we are not in this situation, then we can exactly describe the obstruction in the following way. So let's assume that you have any non-singular Bernoulli shift. We assume that mu is not atomic, and we assume that we are not in this type 1 situation. Well, then actually, essentially we are just saying that the shift must be ergodic and has an infinitely divisible associated flow. Although there is still one little nuance, which you can always realize. The nuance is there exists in your base set X0 a unique, up to measure 0, subset C, for which the remainder is summable. And of course, if you had your fixed C, you could always add a remainder and give it a weight that is summable. So this is something that you cannot avoid. So there exists a subset C with the remainder having summable measure, such that on C to the Z, we have such an ergodic Bernoulli shift. Thus, we have an ergodic Bernoulli shift with infinitely divisible associated flow, and on the remainder we just have a fundamental domain. So that's the general structure theorem. And so in particular, the theorem is saying that for any ergodic Bernoulli shift, the associated flow must be infinitely divisible, yeah? Because then the C will be X0. So every ergodic non-singular Bernoulli shift has an infinitely divisible associated flow, and it's already a result that goes back to, that was proven by Giordano, Scondalise, and Woods, that not every ergodic flow is infinitely divisible, and actually there are infinite tensor products of type 1 factors whose flow of weights cannot be divided by 2, and this was actually the way in which Giordano, Scondalise, and Woods proved that there are infinite tensor products of type 1 factors that cannot be written as infinite tensor products of 2 by 2 matrices. So ITPF1, 2 is a strict subset of ITPF1 due to them because of this result of not dividing by 2. Now I have one technical slide to give you some idea why for a Bernoulli shift the flow must be divisible, say, by 2. Let's not technically divide by n, but let's divide by 2. So here it goes, because there is one very beautiful idea that's in the back of this, and that's due to actually mainly Kozlov and Danilenko. So consider your arbitrary shift, and we will assume that the measure is not atomic as before, but let's also assume that there is no fundamental domain, that the action is conservative, is recurrent, so there is no part of type 1. Now, what is the shift doing? The shift is, of course, permuting the coordinates by shifting. Now, we can also permute the coordinates by the finite permutations of the index set z. So for any permutation of z that only moves finitely many points, we can permute these coordinates, and then this group S is acting by non-singular transformations on x mu. And both have a Maharam extension. For both you have the Radon-Nikodym derivative of the action, logarithm, skew product, and so on. Now, one may feel, but this is, all the difficulty is there, one may feel that the shift by 1 can somehow be approximated by a permutation of a finite set where you take the finite set large enough, but the whole difficulty is there. It's not true in general, anyway. But nevertheless, doing a very careful approximation, you can, under just these assumptions, but the assumption of conservativeness is needed. Without conservativeness, it's wrong. So, under the assumption of conservativeness, the z-invariant functions under the Maharam extension for z is the same set as the s-invariant functions on x times r, because of this approximation of shifting by 1 with a finite permutation. Even more so, the same argument will say that if you only consider shifting by 2, shifting by 2 will also have the same invariant functions as shifting by any finite permutation. Now, if we do the following now, divide z in the even part and the odd part, both correspond to somehow the infinite product you write as the product of the even times the product of the odd, and on both you have finite permutations only permuting the even part, only permuting the odd part. And now we can have a whole chain of inclusions. So the z-invariant functions is the same as the s-invariant functions. That's of course contained in the functions that are both under finite permutations of the invariant under even permutations and odd permutations. By the argument there, that's the same as being invariant under translation by even integers on the even part or by even integers on the odd part. And then this is contained in just translating by even integers, and that is the whole trick, of course, that divides by 2, that is still equal to the z-invariant functions. So we have a whole chain of inclusions that must be this all equalities, and this is essentially saying that the associated flow of the z action will be the join of the associated flow of the even part and the associated flow of the odd part. Now, because the shift by 1 under this Kakutani criterion doesn't do much, I mean, the even part and the odd part are just conjugate actions, so they have the same associated flow. So we really have divided the flow by 2. Now, this is an extremely rough outline because the whole analysis is hidden in how you make these approximations actually work. But it does give you an idea where the infinite divisibility comes from. So that's the abstraction part. So now I want to go to the construction part, why many flows can be realized. And for that I need a little intermezzo, because they will have to do with variance of Poisson boundaries. Of course, we will not look at the Poisson boundary of the real line, because that's R is amenable, it's trivial, it will be periodic or trivial. But we will rather look at random walks on the real line where the transition probabilities are time dependent. So let's look at a probability, to a random walk on the real line, where at time n, you move by a certain number to the left or to the right, and the step of the random walk is governed by a probability measure eta n, and of course you take the steps independently, so therefore the random walk, let's say that we start with a probability distribution that's equivalent with Lebesgue, and then at step n, the distribution will be this convolution product of the measures eta 0 up to eta n. Now, in exactly the same way as one usually defines the Poisson boundary of a random walk, there is a natural Poisson boundary when you have this time-dependent random walk. It will be by construction an ergodic flow. It was defined by Kohn and Woods at the end of the 1980s. And why did they consider this? Because they proved that these, say, we call them tail boundary flows, that these flows, these kind of Poisson boundary flows, they are precisely the flows of weights of ITPF1 factors. So infinite tensor products of type 1 factors, where you can imagine what happens. A type 1 factor is of course B of L2, and you have the probability, the state on it, which you can diagonalize. This will essentially lead you, by looking at the proportions of the eigenvalues, to certain discrete probability measures on the real line, and these discrete probability measures on the real line will serve as the transition probabilities, and then you prove that the flow of weights of the ITPF1 factor is precisely this tail boundary flow of the random walk. They also characterized in purely dynamical terms which ergodic flows arise in this way. These are precisely the so-called approximately transitive flows. So transitive would be, of course, R acting on the real line or the periodic flows. And there is a version of being approximately transitive, and that is exactly what happens as tail boundary flow. Okay, so this is the definition of a tail boundary flow. And how is this related to Bernoulli actions? So let's again look at a conservative and thus ergodic that follows from our theorem Bernoulli shift. And here is a crucial lemma. So assume that your measures mu_n have in a sense a limit, but in a very weak sense, when n tends to infinity. Namely, there exists a measure, it need not even be a probability measure. There exists a measure mu, equivalent with mu0, such that pointwise, the logarithm of the Radon-Nicolson derivative will almost everywhere pointwise converge to 0, so the Radon-Nicolson pointwise converging to 1. Well, if that happens, then we can compute that the associated flow of the shift is precisely the tail boundary flow of this sequence of probability measures, where you push forward mu_n was a measure on x0, you push forward mu_n to the real line with this function theta n. So this produces you a sequence of probability measures on the real line. Its associated tail boundary flow is precisely the associated flow of the Bernoulli shift. Now, this of course will give you somehow a feeling that thus every tail boundary flow should arise as the associated flow of the Bernoulli shift, because this is kind of an arbitrary sequence of probability measures. Indeed, it is. But in order for this to be the associated flow of your Bernoulli shift, we need this shift to be conservative. And there is really an important tension that I will try to explain with this non-singularity and conservativeness hypothesis. Because, as I said, mu_n plus 1 should be close enough to mu_n. So on large intervals, the measures mu_n should be almost the same. Now, if on large intervals, the measures mu n are almost the same, it means that on large intervals, these transition probabilities are almost the same. Now we know that the usual Poisson boundary of the real line is trivial. So if you repeat for a long, long while the same transition probability, this will typically make your Poisson boundary trivial. Unless, of course, you make sure that the transition probability is very much localized around zero, in the sense that, ideally, if you want to transition for a very long period by the same transition probability, you could do that if the n-fold convolution power of this transition is still reasonable. Indeed, if this n-fold convolution power is a reasonable measure that we had a priori divided by n for convolution power, you can do things. Anyway, to cut a long story short, you start feeling that we better have such transition probabilities that can be divided, infinitely divisible in the usual sense of the word for probability theory, or infinitely divisible laws, and that's what will come up now. So indeed, we can have such associated flows that are tail boundary flows precisely in the case that we call Poisson flows, namely tail boundary flows for transition probabilities that are Poisson distributions. So let me define this, if you're not familiar with that. So this is again on the real line. So we call Poisson flow every ergodic flow that you can realize as the tail boundary flow of a sequence of very specific transition probabilities. And depending on your taste, you could do it right away with the traditional Poisson distribution. So what is eta of A lambda? It's a discrete measure on the real line that has only atoms in multiples of the real number A. And then the weight of that multiple of A is given by this Poisson distribution. But of course, you could also do it more generally. That's what they usually call compound Poisson distributions. You could take, given any finite positive measure on the real line, you could take its exponential for convolution powers and then normalize so that you get a probability measure. So that's what they usually call a compound Poisson distribution. And what we look at is tail boundary flows, so Poisson boundaries for these random walks on the real line, where each transition probability is such a compound Poisson distribution. And of course, the regular one is a special case of this one, yeah, where gamma n is just the Dirac measure in an with the right. Okay, so what is the theorem? This is the constructive theorem. Whenever you have an infinite amenable group, the word amenable now somehow appearing for the first time, I'll get back to that. And for any Poisson flow in that sense of the word, we can construct a non-singular Bernoulli action that is ergodic and for which the associated flow is this Poisson flow. So all Poisson flows can be reached by non-singular Bernoulli shifts of any amenable group, and you can do this not necessarily with x0 being 2 points, as I mentioned, but x0, an infinite discrete set, is enough to realize this. Okay. Now, here is a little nuance and a link to ITPF1-2 factors, so infinite tensor products of 2 by 2 matrices. If, which you were maybe already assuming, we would only restrict to Poisson distributions where the A is positive, which is what we are used to. I mean, usually we don't take Poisson on -a, -2, and -3, but I mean, it could have been. And we were not assuming it. But if we assume it, or if you take this compound Poisson distribution where gamma is only supported on the positive reals, we say that we call this a Poisson flow of positive type. And why is this important? Well, here is again the definition of an ITPF1-2, as I said. The point is that the Poisson flows of positive type are precisely those flows that arise as the flow of weights of an ITPF1-2 factor. And what we also proved is that any almost periodic flow is realizable as such a Poisson flow of positive type. And this, for us, was remarkable. First of all, it was remarkable for us that this was open. So it was an open problem left back then when ITPF1 factors were popular, to prove that any almost periodic flow is actually the flow of an ITPF1-2 factor. So that's also one of the corollaries, that there are many more ITPF1-2 factors than were known before, but then also for any almost periodic flow, we do have a non-singular Bernoulli action with this flow as associated flow, or as flow of weights. Now here is an interesting thing. So how can you go, for instance, from, say, a negative type to a positive type Poisson flow? By just reversing time. I mean, if I have an action of the real line, I can look at the action of minus t. And here is, to me, a very intriguing open problem. If I give you an ITPF1-2 factor, and I reverse its flow of weights, I don't know whether this is still an ITPF1-2 flow. And this is quite remarkable that this seems to be really a difficult problem. Okay, so this is on the constructive side. So for any amenable group, any infinite amenable group, you have these Bernoulli actions with lots and lots of possible flows, in particular all almost periodic flows. So now I have to say a few words on Bernoulli actions of non-amenable groups, where actually the situation is quite a bit different. So again, there is the Kakutani criterion for non-singularity. It remains the same. So the action is non-singular if and only if, for every fixed element in your group, the distance between mu of gh and mu h will be square summable if we take again this Hellinger distance. Now, if you remember the definition of the Hellinger distance, which was this L2 distance between two vectors, you actually already see that by construction, this Kakutani criterion gives you a one cocycle for the group with values in L2 of G tensor L2 of the base space, where on L2 of G we are acting by left translation. So the initial data of a non-singular Bernoulli shift comes with a one cocycle into the regular representation. So therefore, and this is actually really not so hard to prove, it was an observation made by Jonas Wahl and myself several years ago. So in the non-amenable case, if the first Betti number, L2 Betti number of G is 0, then all such one cocycles must be coboundaries, almost by definition of what it means to be non-amenable with 0 first L2 Betti number. And therefore, if you have a non-amenable group with 0 first Betti number, then any non-singular Bernoulli action is simply the disjoint union of something with a fundamental domain and a probability measure preserving standard Bernoulli shift. So no type 3 behavior at all if the first Betti number is 0. Now on the opposite side, on the constructive side, with Michael Björklund and Semir Kozlov, we proved that if the first Betti number is positive, then actually you can get type 3. So then there do exist non-singular Bernoulli shifts of type 3-1. Now this is, of course, again, such an existence kind of result. And if I formulate it like this, so I will now try to present you, but these are much less definitive results, try to show you a few results that give you criteria for ergodicity and type for such a general Bernoulli action. Now, it's less understood than for the case of Z, and it gets a little bit more messy. So here is a first assumption we have to make. We have to make the assumption that somehow the base measures mu g are not too wild, in the sense that the Rado-Nikodym derivative should stay away. Well, if you take the logarithm, it should remain pointwise bounded. It should stay away from 0 and plus infinity, but in a pointwise way. And here it will turn out that there is a very big difference between assuming this pointwise and assuming this uniformly over x0. It will completely change the possible behaviors of the Bernoulli shift, and that's where the difference between a finite and an infinite base space comes from. Because of course, if x0 is finite, then having it pointwise or uniformly is the same thing, yeah? Okay, anyway, let's assume this kind of tameness thing pointwise. So, first thing, so remember, the data, the Kakutani criterion gives you a one-cos cycle. So there is this one-cos cycle with values in the regular representation, and it's very common in geometric group theory to then look at the norm square of such a one-cos cycle, and then take this kind of positive definite function that goes with it. Well, if the one-cos cycle somehow grows too fast, or not very slowly is maybe the better expression, in the sense that this becomes finite, so if the growth is a bit too fast, so that this is summable, then we prove that the shift is dissipative. So there is a fundamental domain, type 1, not in each state. So in order to go beyond type 1, we need the shift, the one-cos cycle to grow slowly. So ideally, of course, you would now have a result saying that, well, you can dream and say if the sum is plus infinity, then the shift is ergodic, but the world is not as nice as that. So we have to replace CG by another quantity, and if that one sums up then to infinity, then the shift is ergodic. So here comes the messy thing. We have to replace the Hellinger distance. So recall that this has to do with the Hellinger distance between mu of GH and mu H. We have to replace the Hellinger distance by something else that's not even a metric, but something that does measure a distance between mu of GH and mu H. Namely, we look at this Radon-Nikodym derivative, we integrate, we logarithm, and we sum up. It is somehow saying how close mu of GH is to mu H, because if they are equal, then this integral is 1, the logarithm is 0, so you see things are good. And then the theorem is that if such a sum is plus infinity, which is of course not the contraposition of this one being summable, but if such a sum is plus infinity, then everything is nice. Then the shift is ergodic, you have a formula for the type, it's never type to infinity, it's never type to 0, so you're always in say the regular cases, it's type 3 lambda with lambda strictly above 0, and moreover, and I will give you in a minute the definition of this group theoretic thing, if G has only one end, then also all the type 3 lambdas are excluded. So if we have the group non-amenable with only one end, then but it's under this assumption, and under that famous assumption, no way you can realize anything else than 2-1 and 3-1. This is just what can happen. And I must say, why is it for us so difficult to go beyond this? We have no single possibility to calculate type or associated flow without an assumption like this one. So yeah, this remains a mystery. Okay, so let me explain what is the notion of an end in a group and then formulate some open problems to conclude. So ends in groups, that has to do with almost invariant subsets. So if you have a subset in the group with the property that the symmetric difference between a translate of that set and the set itself is finite for any group element G, and we say that W is an almost invariant set, and there always are almost invariant sets, namely the finite ones and their complements, the cofinite ones. And if these are the only almost invariant sets, then you say that your group has only one end. Now, groups with more than one end have a very specific group theoretic structure. So that's the theorem of Stallings. They are essentially amalgamated free products and H&N extensions. There is not so much you can do in order to get more than one end. Okay, so here are now the questions to put up. Is there a non-amenable group with a Bernoulli action of type 2 infinity or type 3 0? My guess is really that these do not exist, but we can only prove this under these tameness assumptions on the measures. Is there a non-amenable group with only one end that has a Bernoulli action of type 3 lambda? Again, my guess is no, and again, we only proved it under the same tameness assumptions on the measures. And then the more tricky one. Take a non-amenable group with more than one end. Does it have a Bernoulli action of type 3 lambda with arbitrary lambda? Well, here I really have no idea, because what we could prove is that they do have Bernoulli actions of type 3 lambda, but only with lambda close enough to 1. And how close to 1 has to do with how the free or amalgamated free or HNN decomposition of Stahling's theorem is really looking like. So here, I mean, this gets very subtle, it seems. So I wouldn't dare to make any guess here. And with these open problems, we'll stop. Thank you.